Hello, DAC58 attendees, and welcome to Spillbox presentation. My name is Yasmin Ayanovic. I'm Chief Innovation Officer at Spillbox. And today I will give you an overview of the new file system that allows automatic expansion of EDA workloads across data center and cloud. Let's start with a brief introduction of our team. Alok Sinha is a veteran of EDA industry and CEO of Spillbox. His 25-year work experience spans across EDA tools, system software development, and enterprise IT management. Rajiv Prasad, Chief Operating Officer. He brings a wealth of experience from his work across leading semiconductor companies like Intel, NVIDIA, and Synopsys. And also a bit about myself. I have been working on product and technology development for over 25 years at Intel and Qualcomm. So let's start our presentation with short background. Modern cloud computing has been on a rapid rise since the early 2000s, and many industries and applications have moved entirely to the cloud. However, there are still entire industry segments such as EDA and semiconductor development that primarily rely on traditional on-premise private data center computing. To meet the ever-increasing peak demands, these industries require computational scale of the cloud. Otherwise, they're stuck in the cycle of trying to expedite compute hardware upgrade cycles while managing a high capex cost. So migration to the cloud is necessary, but it does impose some big challenges in terms of managing software legacy and preserving application workflow while dealing with very complex and large data sets. It also brings the need for special operational skills for fully automated solution. According to industry papers and articles quoted here, there's a 1/3 of the cloud migration that fails and 2/3 that takes longer than a year. Here's where cloud bursting emerged as an alternative solution with partial and temporary move of workloads from on-premise to the cloud. Still, cloud bursting brings new set of challenges, and that is what we will discuss in the following slides. What are the challenges associated with the cloud bursting approach? First, to avoid rewriting the applications and to enable easier use, we need to recreate the data environment. This is typically done by copying and mirroring the data. However, in the case of large data sets, that is impractical due to significant time required for copying. Also, cost of cloud storage needed for duplication is prohibitively high, making the cloud bursting solution less compelling. To reduce storage cost and to improve data access latencies, potential solution is found in data caching. In order to achieve performance improvement, some solutions rely on proprietary hardware, which, depending on data access patterns and on the network file system protocol, may still not be adequate. And for mainstream solutions that use standard NFS protocol, the overhead associated with the metadata access over the WAN remained to be the bottleneck. This was recognized by Spillbox, which developed patented technology solution to remove this obstacle. The core of Spillbox solution is SPLFS, a high performance file system that is instantiated per application and which improves application performance through intelligent caching of metadata and file data. The SPLFS extends the cloud bursting concept also to remote data centers, and by allowing mix and match combinations of data center and cloud resources. It supports dynamic aggregation of compute resources as shown in example above. Since the core solution is based on caching, the majority of data remains at the source, i.e. in this example at the premises of data center A. And only a working data set used by application is copied to cache along with the corresponding metadata. So in summary, what is new that Spillbox brings to the solution space? First, there is a file system that is dynamically created for an application instance. Second, there are caches associated with each instance of file system to accelerate the performance of an application instance. Third, SPLFS allows scaling of file system resources for hot data, where data can reside either in a system memory or in the storage such as SSD. And lastly, SPLFS server fetches data automatically on a need basis from source over the WAN. Now let's go over more detailed visual representation of what we have discussed previously. Starting from the left, the petabytes of data residing in the on-premise storage become instantly visible to the application in the cloud as soon as corresponding SPLFS instance is created. As the application workload executes, requested data is automatically brought into the SPLF cache, which can be instantiated in either system memory or in locally attached SSD, or even in a cloud service provider supplied object storage. As execution proceeds, the SPLFS cache warms up and application workloads start seeing performance benefits of fast access to the working data set. We will illustrate some of these points in the following slides. Now first, let's expand the previous diagram with some more details. We see here that from the so-called control plane perspective, the connection between on-premise and the cloud is established using standard job management software like Slurm or LSF, which are responsible for spanning off the application workloads on the cloud side. From the data plane perspective, the link is established between the data storage agents running on the on-premise side and the SPLFS instance running in the cloud. Now, the requested file data as well as relevant metadata can flow between the on-premise source and SPLFS cache. To further optimize the SPLFS and application workload operations on the cloud side, an analytics engine can be implemented using information supplied by the cloud service provider. The approach of cloud bursting using Spillbox infrastructure has been tested by multiple customers. And in one particular example, a semiconductor design implementing Bitcoin mining engine was used as a benchmark. The table presented here shows the test setup with an equivalent hardware and software infrastructure running the test workload. First on premise, like in EDA vendor data center to establish the baseline. After that, workload is run on AWS without the Spillbox. In this case, data and workload have been migrated manually. And third, we have AWS with Spillbox configuration using cloud bursting and SPLF caching. Now let's see what kind of results do we get with this benchmark. In terms of performance, the table shows through several metrics that SPLFS accelerates execution of Bitcoin design workloads as compared to the baseline for 7.6% and for 9.7% as compared to running the same test fully migrated to AWS without Spillbox. It is important to highlight that SPLFS caching reduces the total amount of storage required to contain the workload data down to a almost trivial amount, and we will see that in the next slide. To conclude, let's highlight the storage reduction benefit in quote customer testimony on operational efficiency of the solution. We see here, based on a list of 3 data directories that are part of the tested design example, that there's a huge reduction of data storage requirement in the cloud down to 10% of the original data set at the on-premise. Also, the automation that Spillbox provides results in a large reduction of man hours, and according to customer testimony, down to 10% of time required for manual migration of the workload. We will wrap up this session with a summary of benchmark results and benefits as seen by the customer. First, ease of use. Spillbox allows to run existing EDA workflows after completing a very simple one-time setup. Second, storage requirements in the cloud are reduced for 90%. And third, performance is measured by execution time is improved by almost 10%. Thank you for viewing this video. And if you're interested in additional details, please attend presentation session or see authors in the Spillbox booth.